we'll discuss the second part of the fundamental theorem of calculus. For this, we need our function to be continuous over the interval from a to b. Then for every t inside of that interval a to b, the derivative of the integral from a to t f of x dx is equal to f of t. Essentially, what this tells us is that the integral is in fact the antiderivative. So far, we've been taking advantage of that fact, but this is the formal statement that the integral and the antiderivative are in fact the same thing. Let's look at this integral or antiderivative. And you'll notice this is set up in the form of the theorem with the variable t at the top. If we take the integral, we would add 1 to the exponent and then divide by that number. Negative 2 divided by 2 is negative 1. Then the integral of 7 would be 7x. And we're going to take that between 0 and t. Sticking in the upper bound would give us negative t squared plus 7t. And then minus, sticking in the lower bound, negative 0 squared plus 7 times 0. So we get negative t squared plus 7t as the antiderivative for this particular problem. We'll now repeat this integral, but this time we'll start at negative 3 to t and see how it changes. Our derivative would still be negative x squared plus 7x. This time we go between negative 3 and t. We have negative t squared plus 7t. Sticking in negative 3 would then be negative 3 squared plus 7 times negative 3. This gives us negative t squared plus 7t. This first thing is negative 3 squared is 9. We have a minus and another minus, so plus 9. This last term would be minus 21, and then we are subtracting that, so plus 21. We get negative t squared plus 7t plus 30. Essentially, whatever the lower bound is tells you what your constant value is that you'll be adding to the end of this problem. And this actually gives us the area function. So for instance here, if we have an area that starts at negative 3, we can pick our upper boundary point, stick it into this function that we just found, and then we have the area. We're now going to use the second fundamental theorem of calculus to solve this, which looks very complicated. In fact, we haven't discussed how to integrate something like this yet. But we can do it because we are looking at the derivative of the integral, and derivatives and integrals cancel each other out. And in fact, we would just be left with sine of ln of 2t minus 3. And that would be the derivative of this integral, since the derivative and the integral will cancel. Now let's try this one. This one differs slightly because of our upper bound that has a 7t. Essentially, we're going to do a slight substitution. We'll let u be equal to 7t. So now we have the derivative from 3 to u. And this looks closer to what we want it to. We no longer have something built in. However, if we call this original function f, our chain rule actually says the derivative of f of t would be the derivative of f with respect to u times du dt. So essentially what this says is if we want to find an antiderivative with something like 7t as the upper bound, we would have cosine of e to the 7t minus 7 times 7t, and that would consider the df du. The du dt is just the derivative of u. So we would then multiply by 7. For this one, you'll notice our function with t is now on the bottom of the integral. However, we actually have a problem or a property that says if we switch the bounds, all we have to do is change the sign of the integral. And now it looks better. We would then have negative e to the ln of t. And then we would have to multiply by the derivative of ln, which is 1 over t. So this ends up being negative t times 1 over t, which would just be negative 1.